Hi again, welcome back to the Physics Bible. In this video we're going to look at CP3 from the Edexcel Physics GCSE, which is the conservation of energy topic. Don't forget, you can do this. Okay. Starting with the definition. What is the law of conservation of energy? Remember that you should try and pause the video, answer it yourself, and then check. So the law of conservation of energy is that energy cannot be created or destroyed. It can only be transformed, which means changed, into a different energy store, which is basically an energy type. This is one of the new terms that the exam board are going to be expecting you to use. Now, if you're someone who's doing your GCSEs now and this is the first time, you may not know any different. But if you've been using other websites or other exam boards or the old specification, you might not have heard the term energy store. We're going to look at what that is in the next question, but be aware that that word is very important in this topic because it's been a change. I'm expecting the exam board are going to want you to use it when talking about energy transformations. So part B, name 6 energy stores and 4 methods of energy transfer. The first ones are done for you. So an energy store is exactly what it sounds like. It's a form of energy, and energy is contained in that thing, or it's kept in that thing. Now, when we say contained or kept, it doesn't mean that it's in a box. It doesn't mean it's in a tin and we've got some energy in a tin. In this case, nuclear energy, it means that every nucleus of every atom has the potential to release energy. Therefore, nuclear energy is the store of energy in the nucleus. An energy transfer is how we could actually change this energy into a different store. So what methods can we actually transform the energy into a different energy store? So see if you can fill them out yourself, and I'm going to go through that in a couple of seconds. Let's start with the energy stores. So we've got nuclear. The other 5 are chemical energy, movement, or what we call kinetic energy, heat or thermal energy, strain, or sometimes referred to as elastic potential energy, and finally gravitational potential energy. So those are how energy can be stored. An example of chemical energy could be petrol. Okay, the potential for energy to be released is there. Kinetic energy, if something's moving, often on Earth it's quite difficult to see this store of kinetic energy because friction tends to take the kinetic energy and transform it into different things. But if you imagine you're in space and you throw a tennis ball in space, then once you've thrown that tennis ball has kinetic energy, and actually it will keep that kinetic energy and keep travelling forever unless some other force causes it to stop. So kinetic energy can be an energy store as well. Thermal energy, everything in the universe contains thermal energy. It's just that hot things contain more than colder things. Even ice contains thermal energy. I know it seems cold to me and you, but technically 0 or -1, well, there's going to be a lot more energy in ice at -1 than there is at ice that's -100. So if you think of it that way, there must be more thermal energy in the hotter ice. 5, strain energy. Things that are stored in elastic objects. Now that's not just an elastic band. That can be any material which has got a bit of give. Just elastic things are much easier to see that type of energy. That's also linked in with springs, which is in your paper 6 topic. Gravitational potential is the energy of anything that is lifted up a height. The higher and heavier something is, the more gravitational potential energy it gains as it moves up. How can we transform them from one form to another? By a force is one of them. The other 3 are by light. Now it doesn't have to be visible light, it could be radio light, radio waves. Anything in the electromagnetic spectrum transforms energy, or at least moves energy from one place to another. So when you turn a radio on, for example, it's the radio waves that are transforming, well, they're carrying the energy to your radio. Probably the one that we're most used to seeing examples of in the house are by electricity. We know that obviously electricity gives our devices energy. That energy has come from somewhere. It's come from a power station, which was actually created energy from a chemical energy store in things like coal. To get the energy to our devices, we transform it by electricity. And finally, by sound. So these are the things that we should think of them as energy stores, and these are the things that can actually transform them from one to another. So why don't we think about this one? Describe the energy changes that happen when a car accelerates. So for this question, you want to think about what store of energy is there at the start, what does it get turned into, and how does it actually do the transformation. Have a go yourself and then check in a second. Okay, so it's sometimes good to actually draw out what the energy transformation is. In this case, we will be starting with a chemical energy store. That's the petrol or the diesel in the car, and that's going to be transformed into kinetic energy. How does it do it? Well, to actually get the car to move, there must be a force. We know that it's a resultant force that causes a speed up or slow down. So we're going to say that the chemical store is transformed into a kinetic store by a force. If we wanted to elaborate a bit more, we could also point out that energy is wasted by sound and thermal. Now that's not staying with the car. The sound of the engine and the heat of the engine and the friction from the tyres, that's actually going to be transferred to the surroundings. So we're just going to refer to that as wasted energy by sound and thermal. Describe the energy stores and transfers when you climb a cliff and then jump into the sea. So let's split that into two. See if you can do an energy diagram for A, when you climb a cliff, and then B, when you jump into the sea. Okay, so let's look at when you're climbing a cliff to start with. Well, if you do something as a person, what powers you is food or fuel, and that is a store of chemical energy. That's going to be transformed into gravitational potential energy as you're climbing up. How do we do that? By a force. When you then jump off the cliff, we're converting gravitational potential energy, which we gained from converting the chemical energy, and that gravitational potential is being turned into kinetic energy, movement energy as we fall. And the further we fall, the more the gravitational potential energy is being transformed into kinetic energy, and the faster and faster we get. How is that being transformed? Well, also by a force. The weight the weight force is actually going to accelerate the person jumping off the cliff downwards. Again, we can think about it a step further, and when you actually land into the sea, what's happening? Well, there's going to be wasted thermal energy and sound energy and kinetic energy. The kinetic energy of the water is going to be wasted. The water is technically going to be heated up by the fact that you're smashing into it, so that's wasted energy, and there's going to be sound as well. There is a bit of a pattern to it. You can see often the forms of wasted energy are thermal and sound, and that's mainly because friction is what causes a lot of transfers of energy. The next one, in question 18, we've got an equation which is efficiency equals useful energy transferred divided by the total energy supplied. So this can be applied to any energy question. It could be, it could even be applied to, an electricity question where you know how much electrical energy has been transformed usefully and how much electrical energy you supplied. And actually, this is the case in our first question. A light bulb transfers 100 joules of energy by electricity to light and heat. 70 joules of light energy are produced. What's the efficiency of the bulb? So it transfers 100 joules in total, and it transfers it to light and heat. "70 joules is light. How much energy must be transferred by heat? Well, due to the conservation of energy law, we don't lose any. So if 70 has gone to light, then 30 must have gone to heat. So before, we've got 100 joules being transferred by electricity, and after, we've still got 100 joules of energy, but they've been transformed into light and heat. Now for the efficiency calculation. The efficiency, which I'm just going to write EFF, the efficiency is the useful divided by the total supplied. In this case, why do you turn a light bulb on? You don't turn it on to actually get the heat from it. You don't want to heat up a room. You want it for the light. So the 70 joules is the useful energy, and the total supplied was 100. which means the efficiency is 0.7. And that's a final answer, efficiency of 0.7. You can turn that into a percentage by timesing it by 100, which means that the light bulb is 70% efficient. The next one is similar, but this time we're going to have to rearrange the efficiency equation. An LED bulb is 90% efficient. How much light energy will be produced if 100 joules are supplied? Let me just write the equation out. Useful divided by total. So we've simplified the equation. We are trying to find the amount of light energy. Now, which letter does the amount of light energy represent? Well, the light energy is the useful part. We've been given the efficiency. We've got the efficiency. We need to find the amount of useful energy. 100 joules is supplied, so we've got the total energy. So to find the amount of useful energy, we'll have to rearrange that equation. Have a go at that. Be careful with the 90% and make sure that when you put it in as a number, you put it in as the decimal. So if 70% is 0.7, then 90% is, well, have a go yourself, see what number you get. Okay, so rearranging this, useful equals the efficiency number multiplied by the total amount of energy. So the amount of useful is 0.9, that's 90%, times by the total we put in, which was 100, so our final answer is 90 joules. So if the bulb is 90% efficient and you put 100 joules in, then the amount of light energy you'll get out will be 90 joules, which means that the amount of heat, which is the wasted part, must be 10 joules. 10 joules has to be wasted because the useful plus the wasted has to equal what you put in the first place. Conservation of energy law. Part C. Oiling the chain on a bike increases efficiency. Explain why. So this is to do with friction, and it's to do with wasted energy and useful energy and how much you put in. So have a think about riding a bike if the chain on it is really sticky, maybe full of mud, and then think about it if it's nicely oiled. We can also use the word lubricated for that as well. Can you explain why an oiled chain increases the efficiency? You're going to have to use these types of words. You can't just say because it's easier. That is obviously part of the answer, but you've got to link it to efficiency. Have a go and we'll go through it. Okay, so explain why it increases the efficiency. If we've got to explain about efficiency, then we want to be using the words useful energy and also wasted energy. So if we put energy into cycling, the chemical energy in our body is transformed to kinetic energy by a force. Now, if riding the bike was 100% efficient, then all of the energy from the chemical energy in our body, all of it would go to kinetic energy. So all of the energy all of the effort you put in would be turned into movement energy in the bike. The problem is that if it's not oiled, less of that energy is actually going to be put into kinetic energy, and some of it's going to be wasted as heat and sound because of the friction on the chain. Now we've got to make sure that we stick to answering the question. So it actually wants us to talk about why it increases efficiency. So we can say by oiling the chain, this reduces friction, and so less energy is wasted by heat and sound, and more is transformed to kinetic energy. And I'm running out of space, but I'd like to say which is useful at the end. So if we oil it, then our useful energy is going to be a big number, so the efficiency is going to be big. If we don't oil it, then there's going to be more wasted as heat and as sound because of the friction on the chain, so our useful energy is actually going to be less, and therefore the efficiency is going to be less. The total energy supplied, well, that's a constant. It's only fair to compare it if we're actually talking about putting the same amount of energy in. So exactly the same test. One cyclist puts in the same amount of energy into a rusty bike, one puts it into a well-oiled bike. The well-oiled bike is more efficient because there's less friction, so there's less wasted energy. We're now moving on to methods of energy transfer, and these are the three big energy transfer methods. Now, I strongly recommend that you go through your revision guide before attempting this. It is quite a large topic in that the questions can be about pretty much anything, because energy transfers by conduction, convection and radiation are happening all the time across the whole universe, and therefore what question might turn up in the exam, you've got to be prepared to apply what you've learnt about conduction, convection and radiation to possibly an unfamiliar situation. So I'd like you to write as many properties of each method as you can. Basically, what do you know about conduction, convection and radiation? Do a little bit of revision and then fill in the boxes. To save time, I've filled in the first box. This is what I'm looking for, and maybe you can adjust what you've done for convection and radiation yourself. So for conduction, if you were to explain to someone what conduction is, you would say it's the energy that's passed on as vibrations, and the vibrations are passed on between particles in a solid. Now it's important to mention a solid because conduction is only a method that we're going to mention when we're talking about energy travelling through solids, because it has to be vibrations. When it comes to these convection and radiation, we're not looking to use the word vibrations. Examples of a good conductor are metals, and examples of a poor conductor would be wood. A poor conductor is also known as a good insulator. So see if you can do a similar thing for convection and radiation. Okay, so for convection, what is it? It's the movement of particles in a fluid the hotter areas, the areas which have the most energy, will rise, and the cooler areas will sink. So this actually happens probably in the room that you're sitting in now. A radiator is actually moving energy around your room more by convection than by radiation. So really, the things on the wall that get hot, they should be called convectors rather than radiators, because what they do is they heat up the air around them, and when they get hot, the particles around them move faster, they become less dense, and so they rise, and that energy is then spread around the room. Once the energy is kind of been more spread out, then those particles have less energy, they become cool, and they sink back down. More air gets heated up, the particles move faster, spread out, become less dense, and so they rise. And so what you get is what's called a convection current, and the energy is being moved around by the convection current. Now this only happens in fluids. A fluid is a liquid or a gas. So basically convection can only happen when particles can actually move around, and that's why we can't have convection in solids. The last one, radiation. This is the only one that can transfer energy in a vacuum, because it doesn't need particles. It can pass through gases, and it can also pass through some solid materials, especially if the material is transparent, such as a window. I mean, you only have to sit in a car on a hot day to feel the heat coming through the window, and that's because the infrared radiation from the sun is able to pass through the window. Radiation can be absorbed, which means it can be taken in, and it can be emitted, which means it can be given off. It's absorbed and emitted best by dull black surfaces. So something like leather seats in a car often tend to get very, very hot, and that's because they're able to absorb a lot of the infrared radiation from the sun, and because they've absorbed a lot of it, they're also able to emit a lot of it as well. Now, the application of these is more important than being able to actually define what they are. So, as a quick recap, remember, conduction happens best in solids. Vibrations are passed on, metals are good at it. Convection is when energy is transferred around a fluid. Now, a fluid can be a liquid or a gas. So it could be when you heat up water, or it could be a radiator heating up the air in a room. And this is going to cause a convection current. The hot area will cause the particles to rise. The colder area will fall, and you'll get a convection current. Now obviously this will be in your revision guide, but just so that we get an idea of it, there's a flame. Around the flame, the energy is going to be transferred to the air particles. They're going to move faster. When they move faster, they're actually going to spread out more, become less dense, and so they will rise. Now, as they move through the room, they're giving energy to other particles in the room, and so as they move across, maybe across the top of the ceiling, they're going to cool down, and they become slower, more dense, and so they will sink. Meanwhile, because air is rising up here, more air is going to be pulled in, and so now we can see we actually have a cycle or a current. Hot air heated up becomes less dense because the particles are moving fast, the air rises. Here, the air is cooler, it's more dense, the particles are slower and closer together, and it sinks and it carries on. The same physics applies to air as it would be in a liquid. You would just refer to the particles in a liquid rather than the particles in air. Okay, a pan of water is heated on a gas hob. Describe how A. energy is transferred to the water from the gas hob, and B. how the energy spreads in the water. Now it's just a describe question, which means that we just have to state kind of what's happening, describe what is going on. If it was explain how energy travels through the pan, for example, you would have to go into details about the particles, and use the words like vibration, etc. But all we're after here is for you to get the right type of energy transfer. Is it conduction? Is it convection? Is it radiation? And through which bits does it happen? So have a go yourself, and then we'll go through that in a couple of seconds. Okay, so for A, how is it transferred to the water from the gas hob? So this is the gas hob. This is hot, just like a gas hob. It's not red really, is it? It's more blue, which means that it's even hotter than if it was red. Blue hot. First of all, the energy is moving from the flame to the metal pan. How's it doing that? Well, probably by convection and radiation, but mainly I'm just going to go with radiation. I'm going to assume there's a little air gap here. So yes, the air around here is going to be heated up, and the particles that are heated up are going to rise, and they're going to then bump into the pan and give their heat energy. But I'm going to stick with radiation, because I know that there's going to be infrared radiation going to the pan. So from the flame to the pan, energy is transferred by radiation. Let's put that on there because it's true. And convection, because there's an air gap there. If there's an air gap, there's always going to be a little bit of convection happening as well. So from the flame to the pan, energy is transferred by radiation and convection. But we haven't actually said how it gets to the water yet. To do that, there's a metal pan in the way. Energy travels through the pan by, now what must it be? So the energy has moved from the flame to the metal pan, but now we want to know how does it get from the metal pan to the water. In other words, how does it move through the metal? You must have got this right. Of course, it's by conduction. So just in that small area we've seen all three energy transfers. Radiation, so the infrared radiation given off by the flame is heating up the pan. The convection, because it's heating up the air around it and the air is passing on energy to the pan. And finally, the energy travels through the metal pan to the water by conduction. The energy spreads in the water. How does it spread in the water? Water is a fluid. The energy spreads by, have you got it yet? How is it moving around the pan? You've got hot liquid rising all around the edges, and there's going to be convection currents all over the place. I can't really draw them on because it would be a really complicated system, but I know that there's going to be areas where the liquid's being heated up, the water's being heated up, it's rising, there's going to be colder spots, but the liquid's moving around so much that eventually all of the liquid will be heated up. If it's a fluid and the energy's moving around, it must be by convection. 21. Explain why an air gap between walls reduces heat loss compared to a single wall. Well, in a single wall, the heat is transferred by conduction. So the energy from inside the house will pass through the brick by conduction, and then it will be emitted on the other side into the cold outdoors. However, if we add an air gap, so you can probably tell by now that I'm not the best drawer. Definitely not the best drawer. But imagine there's an area that you can kind of go through, and in between the two walls is air. Now, air is a good insulator. It's a good insulator because it's a very poor conductor. Energy can't be passed on from particle to particle easily. The only way that air is going to be, transmit energy from the inside wall to the outside wall is by convection. There is a way we can stop that. We're going to look at it in a second, but there's still going to be a reduced heat loss because we can say that air is a good insulator, so less heat is transferred to the outdoor wall. By convection. Oh, sorry. See, even I'm getting it wrong. Always double check, read your answers back. It's easy to mix up words when you're talking about conduction and convection. So in a single wall, the heat is transferred by conduction, and by putting an air gap between two walls. Because air is a good insulator, less heat is going to be transferred to the outside wall or the outdoor wall by conduction. Cavity insulation is a solid filled with air bubbles. Explain why this is even better than the air gap. Well, like I said before, the problem here is although conduction is reduced by the air gap, convection still happens. Energy is still transferred in the air gap by convection. So in that air gap, energy is still able to move around and get to the outdoor wall by convection because it's a fluid and the particles can move around. By filling the air gap with a solid filled with air bubbles, the air particles can't move. Now that's the important bit. If the air particles that are trapped in the air bubbles, if they can't move around, then they can't do convection. So by filling the air gap, the air particles can't move, so convection can't happen. The conduction is still reduced because the solid they're going to use, well, they're not going to fill the air gap with a big slab of metal. That would be silly because metal's a very good conductor and the heat would transfer through it by conduction really quickly. So the conduction is still going to be reduced because the filling is made of an insulator. So the solid that is put in is an insulator, so energy can't be transferred through it very well by conduction, and because the air in it is trapped, we get the benefit of having poor conduction, which is what we want, but we also have the added benefit that because it can't move, it reduces convection as well. Two equations here. This is much more a mathematical part of the topic. As you can see, this is the last 2 pages, so don't worry, I know this has been a long one, but it's also a very important one, and you're guaranteed to get some questions on energy transfer. This first one, a 500 gram box is lifted 2 meters high. What is the gain in gravitational potential energy? Gravitational potential energy is the mass times the gravity times the height. So we have the mass there, 500 grams. It's lifted 2 meters, so we have the height. What is the gain in GPE? Well, I'm assuming we're on Earth, so G is 10 on Earth. They would probably remind you of that in the exam. So, gravitational potential energy equals mass times 10 times gravity times height, which is 2 meters. Now, I've purposely not put this number in because I want you to think about what number that should be. Should I write 500? It shouldn't be 500, because in this equation the mass needs to be in kilograms. So 500 grams is 0.5 kilograms. To do that, you just divide by 1,000. So 500 grams divided by 1,000, 1, 2, 3 is 0.5 kilograms. 0.5 times 10 is 5 times 2 is back to 10. So the total energy gained is 10 joules. Mr. Percy falls off a 100-metre cliff. Again, okay, so I'm falling off a 100-metre cliff and my mass is 70 kilograms. What's my gravitational potential energy at the top? So GPE equals mass, there it is, 70 kilograms. Gravity is 10, and the height of the cliff is 100 metres. So that's 70,000 joules. If I wanted to write that as kilojoules, how much would it be? Hopefully you said 70 kilojoules. 70 kilo means 1,000, so 70 kilojoules is 70,000 joules. How much kinetic energy does he have at the bottom? Now I've left a small space here, so have a think. I'll give you a clue, you don't have to work anything out. How much kinetic energy will I have at the bottom? Well, if I've gained 70 kilojoules of energy by going at the top, then as I fall down, the gravitational potential energy is going to be transformed into kinetic. And if I reach the bottom, all of that energy will have turned into kinetic. So the answer is 70 kilojoules. The energy I've gained by going up will be transformed into kinetic energy as I fall down. This bit here, calculate my speed at the bottom, is related to the kinetic energy equation and the amount of energy that we know Mr. Percy is going to have as he reaches the bottom. Have a go at this yourself. What you have to do is rearrange the kinetic energy equation to get V equals. It's probably the hardest rearranging you have to do in paper 5, so don't worry if you don't get it to start with. Do it a few times, practice, and you'll soon realise that you can get to it in about 3 steps. We're going to start with the kinetic energy equation. the first thing I'm going to do is get rid of the half. To do that, we times both sides by 2. So I get 2 times the amount of kinetic energy is equal to mv squared. Now, the squared bit is the last bit we want to deal with. So I'm going to move the m first. Can you remember what we have to do with that? Because these are multiplied together, the m is going to be moved to the other side, but it has to go on the bottom. So we get v squared equals 2 times the amount of kinetic energy divided by m. The last step is to change the v squared into v, and the way we do that is by taking a square root. So v is 2 times the kinetic energy divided by the mass, and it all has to be square rooted. So let's calculate it. This is going to be the square root of 2 times the amount of kinetic energy at the bottom was 70,000, and we're dividing that by the mass, which for me was 70 kilograms. I recommend doing 2 times 70,000, then divide by 70, and then the number you get, that's the number that you want to square root. By doing it that way, you are less likely to make a mistake on the calculator. So I'll show you what I mean. So I'm going to do 2 times 70,000. We're then going to divide by 70. So we've got 2,000. Therefore, v equals, it's going to be the square root of 2,000. If you're good on a calculator, you can do that by doing square root, and because 2,000 was the last answer I got, I can put ants, which gives us 44.7. And because it's v, it's a speed, meters per second. Or, because you've written the number down, you just then type square root 2000. And obviously you'll get the same number, 44.7. Next, a 5 kilogram box gains 25 joules of gravitational potential energy when put on a shelf. How high is the shelf? So we've been given the mass, we've also been given the gravitational potential energy. It says how high, so that's h. So GPE equals mass times gravity times height. The mass is 5. The gravity is 10, because we're on Earth. The height, oh, I don't know that. So we've reached another point where we'll have to rearrange the equation. We need h equals. So the m and the g are on this side and we don't need them. We want h on its own. So we're going to move m times g. We're going to move all of that. And again, it's going to go on the other side, but underneath the gravitational potential energy. Remember that GPE is just one thing. It's just one number. In fact, we're told what that number is. It's 25. So the height is actually going to be the amount of gravitational potential energy divided by the mass times gravity. We had 25 joules of that, and we're dividing it by the mass was 5, gravity was 10, so it's 25 divided by 50. Therefore, the shelf is 0.5 meters high. Name 5 sources of renewable energy and which of these are reliable. You may be asked to describe the benefits and the advantages and the disadvantages of lots of different types of energy resource. Best way to do this, go through your revision guide and make notes on each and do it in bullet points and try and split it into advantages and disadvantages. The 5 sources of renewable energy that we need to know of. Can you name them all? First one is solar. Second one is hydro electricity. The third one is wind for wind turbines. We've also got tidal power, and the last one is biofuels. What does it mean if it's renewable? It means it doesn't run out. In terms of which are reliable, this is a really important part of deciding how the government decides where to spend their money on sources of energy, because although a couple of these are very tempting, they could be cheap, it could be easy to get a lot of it. The problem is, if it's not a certain weather type, you might get no electricity at all. So solar is not reliable because the amount of electricity you're going to get is going to vary a lot. Hydroelectricity is reliable because what you can do is any kind of water source you can put a dam in the way, collect the water, keep it there, and then you know that you have that water and that you can release it and turn it into electricity when you need. Wind is not reliable either. Tidal is. Why would tidal be reliable? Because the tide moves in and out twice a day. That is a fact. So you can always rely on that. Biofuels, it depends, but generally you could say that biofuels are reliable if you've got a good store of them, because if you can burn them and get the energy out of it and you know you've got it, then it's as reliable as coal. The problem with biofuels is that if there's certain crops that don't do well in a certain year, then you may get a lot less than you would like. So it does depend a little bit on the weather as to how the crops grow. But if you've got the crops, then it's very reliable because you can turn it into electricity whenever you want. Right, that's the end of CP3. We're going to make a video on CP4 next, and that is all about waves. I know you're dying to get started, so I'll see you there.